Good morning, class. I hope you guys are doing fine. And continuing from the last class where we have covered the uniaxial tensile experiment, we'll be moving forward. And for those who have attended the last class, you would remember that we have discussed how the uniaxial tensile tests are conducted, what are the limitations, what are the rules we need to follow, and what kind of information do we get from such experiments. And if you have not seen the class yet, please go to the description below this video and you will find a link for this class. The class is important for understanding the concept that we are going to deliver in the today's class. So without wasting the time, let's start the today's class. In the today's class, we are going to discuss the different concepts of strain. We are going to talk about the stress tensor. We are going to talk about what are the different kind of stresses are there and how they affect our daily life. And we'll end the class with some little derivations and the definition that are useful for our remaining part of the course. So in the first class, we have understood what the simple stress strains are there. But the limitation in the uniaxial tensile experiment is the loading was one directional. So if we take the case of if we take the example of the specimen that we have tested, we can see that loading was in the direction of the axis or the longer dimension of the specimen. But in general, this is not a case. And what happens is you may come up with a situation where you have multiple loads acting from the multiple directions. So in such situation, what we are going to do is we are going to see how it affects the different stresses and how many types of stresses is it going to create. So let's start the class. Let's start with a stress at a point. So how we are going to define stress at a point, right? So as we said that we are going to consider this time loads from the multiple direction. So to generalize this issue, what we are going to see is we are going to select a body of arbitrary shape and we will have a force or a loading condition from the arbitrary directions. So this will make the problem more generalized. So let me draw that thing out. So let's assume this is our three-dimensional body, and let's say this is being acted upon by forces from the different directions. You can choose any direction of your liking, but for the demonstration purpose, we have marked few loads or few forces, and for simplicity, let's name them also. So we are naming them as F1, F2, F3, F4, F5 and so on. Let's call the last as Fn, and we understand that when the load is applied, what's going to happen is the body is going to deform or body is going to resist against the load. So in either situation, a stress will develop in a body. So to analyze this, let's see. And what we are going to do here is we are going to select a plane, an arbitrary plane passing through a body, and let's assume that plane that we have selected bisects the body in two parts, and the area that is exposed, we are calling it as A, again a generalized term. And let me draw the plane also. So let's say this is our plane which has bisected our body of interest in two parts. And now what we are going to do is we are going to consider one part only so that we can show how the forces are looking on that. So let's do that also. So let's take the bottom part of this and let's also select a small area on which we are interested in finding the stress state. So let's say the small area that we have selected represents a small section of the original area. So we are calling it as delta A. And now what we are going to do is we are going to resolve all the forces that has acted on a body in the direction which is normal and tangential, or basically in plane to the selected zone or the selected plane we have taken. So to that, let me draw the forces also. And what we are going to do is we are going to draw the normal force. So it's a normal resultant and we are calling it as delta Fn, and stands for normal. And we are also taking an in plane and we are calling it as delta Fs, because this force is going to create the shear. So we have given the name S. And now the final resultant we are also going to draw, and let's say this is delta F. These are the straight lines. So normal direction, shear direction, and we have a resultant direction. Once we concur that this is our situation where the plane that has been arbitrarily selected is dividing a body in two parts, what we can write about is, just a second, so okay, let me write whatever I have discussed so far before continuing further, so that way keeping a notes will be easier. So what we are going to say here is, so first thing, we have selected an arbitrary shaped body and we are saying that n number of forces are being applied to it. And second step we have done is we have passed the arbitrary plane through that body. Where the cross sectional area is A, we have already shown in the figure. And now in the third step what we have done is we have selected yet another smaller area on that plane which we have marked as delta A, and then we have resolved the forces in delta Fs, delta Fn, and the final resultant which was delta F. So again writing that thing, and these forces are acting along the unit normal and the shear direction. right? Basically unit tangent. And they are acting on the area which we are calling it as delta A. And actually we have to realize that both delta Fn and delta Fs and their magnitude will depend on the selection of a plane that we are going to assume. So if the orientation or the position of a plane changes, then obviously the value of delta Fn and delta Fs changes. Depends on the location and the orientation. So if we have taken this generalized form, then from the uniaxial tensile test that we have seen, we can easily state what the stress at the point will be, because please remember, so far we have selected the area which is delta A, right? We have not talked about a point, but ultimately if you want to consider a point, we can use the limits to the 0, and thus if you want to discuss about the point, then we can say that average stress, average normal stress and average shear stress given by these three simple terms, since the area is involved. And now if we are going to define this area as a point, or we are going to define as a point, then simple thing, as we said, we can use the limits So we are just using the limits and using the directionality of the force. So the question comes, why we are writing this in such a simple form, or why we are even discussing this. We are just mentioning because the reason is that we are moving towards a concept that we are going to introduce, which is stress tensor. And as I'm hoping that you guys are already aware of from your basic maths classes, maths courses that you have taken, what is the difference between a tensor or a matrix. But right now, let me write what exactly it means. Okay, so we are going to write the heading, which is notation for stresses or stress, whichever way you would like to use. And to start with, we will draw the very common diagram again. So, but please remember, as we have said, everything depends on the direction. Whatever we are going to say, or whatever we are going to talk about the stress or a strain, we have to link with a direction, or in other words, we should have a coordinate system with which we can link the body on which we are doing the stress analysis or strain analysis. So now here on the screen you can see we have fixed the coordinate system in x, y and z direction, and now let me draw the cube which we can analyze. So if we say this is our coordinate system, and let's also say that this is a small section of a body in which we are interested in the cube form. You can draw in any shape, but this is simple to draw and easier to understand. So as we know, we have 6 faces of a cube, but since only 3 faces are visible on a 2D projection, we are going to use that. And let me draw the directions of stress before explaining what they are. So on one face, which is parallel to the x direction, we are going to call it as the x face. We have drawn 3 stresses, or the 3 components of stresses. Similarly, a face which is, just a second, which is visible to you on your screen now. We are writing other 3 components. So just a second, let me draw all these. So we are using this essentially a sigma ij notation, in which one index represents something and the other index represents something. So what we are saying is, in case of sigma ij, the notation we are using is, the first index represents the face on which you are applying the load, and second index represents the direction in which the influence of that boundary condition is visible. So to say, just to simplify it, what we can say is, if we have a sigma xx, we can say it will exist as a tensile force So this term, if you look sigma xx, what we are doing is we are applying a load in x direction and we are also finding out the stress in the direction x. So the plane which was normal to the x direction, that is x plane, if we are applying a load on x plane and the stress in the x direction, we are using sigma xx. So the first component is telling you the phase, whether, and it's related to the unit normal. So the sigma yy is acting on a phase which is normal to the direction y, and sigma zz is acting on a phase which is normal to the sigma zz. So this is the convention that we are using for the ease. Now if we look at the figures, since we have a 3 directions, what we can see is we have total number of 9 components that are visible in the figure. And please remember, it's not necessary that all components of the stress will exist. They may not, but we are talking about a generalized form where we are not taking any assumption. So if you want to arrange these 9 let me first write these 9 components. So first bracket represents the stresses which are related to the x phase, means x direction is unit normal to that phase. So we have sigma xx, sigma xy, sigma xz. So this is for the phase which is x phase. Similarly for y phase, or the phase which is for which y direction is the unit normal, we have sigma yy, sigma yx and sigma yz. And lastly we have sigma zz, sigma zx and sigma zy or zy, whichever way you prefer to pronounce. But the more or the most easy way, or let's say most comfortable way, is to arrange a data in a more structured form. And here we can see the simple thing we can use is a tensor where all the 9 components can be symmetrically arranged. So let's say we are creating a tensor, or let's call it T. It's up to you whatever way you would like to use it. So for just writing purpose, we are saying there exists a tensor which has 9 components. And we are arranging all those 9 components in a manner which are easier to understand. So essentially, when we are saying sigma ij, with regards to what we have just written, it means that we are going to extend our I index from 1 to 3 and j also from 1 to 3. And extending this, we'll get 9 terms that will be arranged in a manner of 3 by 3. So a stress tensor containing the 9 components will be achieved. But more importantly, the question is why we are doing this and how it's useful. See, please try to understand that all those 9 components are essential in determining the complete state of stress at any given point. You may or may not have all the terms available with you, but if you want a generalized form, all these terms, whether they are 0 or if they have some magnitude associated with it, will be needed. In case if you have a symmetry, then you may work with the 6 terms only that we are going to see, but in most generalized form, we will have the 9 components. And also please remember, since we are talking about a tensor, stress tensor, any tensor with the rank 2 can be considered as a 2D matrix. However, we know that vice versa is not true. We cannot say that all matrices are tensor. So let's write. So far whatever we have seen, based on that we will say if we need to define a complete stress state, these components of the stress should be known. But in reality, do we need all the 9 components is a different story. But most general cases is yes, we may need them, but for real or real life application or all practical purpose, we have only requirement of 6 components, and we are going to see why we only need 6 components. So when I'm saying for most practical purposes, I mean that for majority of the cases, even though not for all, but for majority of cases, sigma ij can be considered as sigma ji, provided you have only surface forces and body forces acting and the volume equilibrium is maintained. So let me write it out. So if we consider the movements and their sum, we'll also see that part, what does it mean. But if we do that in the equilibrium conditions, we can say sigma yz can be written as sigma zy or zy. Similarly, sigma zx can be written as sigma xz and so on. So we are also writing sigma xy as sigma yx. And let's put any equation here. Let's call it as a equation A just for our purpose. Then if we assume that only surface forces are acting and body is in equilibrium, we have a luxury of assuming sigma ij is equal to sigma ji, and when this happens, we can write our complete matrix using the stress tensor using only 6 components. So same tensor, if we rewrite it based on this assumption, we can write like this. Here we'll write sigma yy, sigma yz, and then sigma zz. And if you look carefully, it almost look like as an upper diagonal matrix, and we are writing only 6 component. Reason is because other components will be the mirror copy of it, and if you want to write them out, I'll just write this here, but since we are assuming that they are identical, they are no longer needed. As we have just written that sigma xz is equal to sigma zx, and if we follow this assumption, then we'll be only needing 6 components to completely define the stress tensor, under the assumptions that we have only body and the surface forces acting on it, and we have a volume equilibrium. So under these conditions we can work with 6, but please remember, if we have, or in certain condition, if there is a couple that is acting on a surface is present, then you cannot have, or you cannot use this assumption. So let me write this out, and then we'll show how the sigma ij is equal to sigma ji. Our body couple, so your above equation or assumption, which we have written as equation A, will not be valid, and you will need all the 9 components again. Okay, so far what we have done is, we said what is the stress at a point and what are the stress tensor components, and under which situation we can assume sigma ij is equal to sigma ji, and in what conditions we cannot have that assumption. So far we have discussed this, but we'll take one case of sigma ij is equal to sigma ji to prove that this assumption is valid when these conditions are met. So we'll be needing this diagram again, the cube. So what I'm going to do is I'll copy it instead of again writing. So just a second, let me select it. Just a second, I'm looking for the selection. The menu is very small here. Okay, let's see if we can select here. It looks like we can, but so far I'm not sure, so we'll keep doing it. Okay, it seems we have selected. Let me copy it and see if I can successfully paste in the required place. So let's say here, okay, it seems to work fine. So now we are going to use the same figure with the requirement that we want to show. Right. So let's assume we'll go to the same block that we are using. This time, instead of using stresses, we are going back to the basic force to show that we can achieve this derivation. So to prove sigma ij is equal to sigma ji, what we are going to do is we are going to use the fundamental equilibrium requirement of the force and the moments. So the derivation is generalized, but we'll take one of the projection for the ease of use. So what we are going to do first is we will convert this stress into the force. Please remember, we are going to use force and the moment equilibrium. So for converting stress into the force, we'll just do a simple stuff and we'll multiply it with the area, right? So you can assume that all the terms are multiplied by area. So delta A is the area, so we have applied force as shown in the figure, right? And now let's select one point just for our purpose only, and what we are going to say is that point is the center of the cube. So if it's a volume, you have a volumetric center which is encircled by the blue. It's a blue point encircled, but it's a volumetric center. So now if we assume that, let me write it again what I am saying, so not to miss anything. When I am saying above figure, I mean a figure which is above this as shown by the arrow. Delta A is the area, so we are saying the face area we are marking as delta A, and the cube is centered around the blue point or the blue point that we have circled. You can call it even a point, let's say point Q for the ease. So now if you use the very basic equilibrium requirement, which is and similarly for the movement, so we are just writing out the required equilibrium condition that you must already be knowing, and we have set them all to summation of all to the 0. So now we can consider any face of this cube, so or the projection. Let's say we will consider the one projection of one face, or let's say we will consider it on the xy plane just for the simplicity. So we are making a 3D problem in a 2D version. So we'll write it out that if we consider the projection of the face on xy plane, and then consider the movement about the z axis, So let me draw that projection also, it will make things clear. So a projection of a cube on a plane is a square, and what we are going to do is we are also going to draw the centroidal, or sorry, the center position of this plane as the blue. I don't think, okay, the color is right. Let me rechange the color. Okay, so now with respect to the z direction, as we are considering the moment, I will just write out all the forces which are acting on it. So acting on the 2D version of our problem, right? So just a second. So sigma y, when I am writing sigma y, this means sigma yy delta A, sigma yx, it is delta A, sigma xy delta A, this should be sigma x delta A, and similarly here we will have sigma yz delta A and sigma xy delta A, and so on. So we have done nothing, we have just written the projection on xy plane. Now if we want to evaluate the movement about the z axis based on this above figure, we can write from the equilibrium requirement which we have already written above. We can say if we are considering the movement about z direction, then we have sigma xy delta A. So this is a force, right? And the distance, let's assume the distance is A for all. So small a, we are marking it as, and similarly for the other direction, since we are finding a movement, we will take sigma yx, and for converting into force multiplied by area, and to convert into the movement, the distance which we are assuming to A. So this is a required equilibrium condition, because we have already said this equation is valid when you have a equilibrium and the only body and the surface forces. So if this condition is there, then simplifying, whatever we are going to get is, if you simplify this box, move the term to the left and do the simple arithmetic, you will finally end up with this term. And this is, even though we have selected a particular face, but this is a generic solution, because now you can even try this on the projection of the faces of cube in yz plane, on the zx plane, whichever you would like to have. So but one thing is, please remember this thing, just a second, sigma xy delta A, right? And this is A, yes, it represents the counterclock wise movement. We are taking it as a positive. If somebody asks from where the sign comes, and the other is right. So now coming back to the thing that I was saying, if we consider the projection on the other planes, whether it's a yz plane or zx plane, then you can easily show. Similarly, for the projection on other plane, you can easily show that, just a second, let me move this page up, sigma yz is equal to sigma zy and sigma zx is equal to sigma xz. So we have seen the condition under which there will be a requirement of all the 9 components of the stress tensor. However, now we also know that under the favorable condition such as sigma ij is equal to sigma ji, we can work with 6 components only. So once we have understood what the stress is, what are the different components of the stress, we are going to see how the stress acts on the arbitrary plane. Okay, let me use the start from the other fresh page, that will be more. Before going any further, we will be refreshing your concepts about the direction cosines, as they are very important in the few of the next topics that we are going to cover. So for this course, we are going to mark them as L, M and N, and it's up to you if you want to use the different notation, but for this course the L, M, N we are going to use. So let's start. So I'm not going to go in details. All I'm going to show you is if we have a coordinate system, the same coordinate system that we have used in the cube, which is, let's say, or we can even change, it doesn't matter, let's change it. And then what you do is you rotate it by something, some degrees, and the new coordinate system becomes x prime, y prime and z prime. Then you can easily find, okay, let me first write the unit vectors also. Let me draw the diagram. I, this is j dot k. Yes, so the way we can relate the projections of x and x prime, y and y prime and z prime is through the direction cosine that we already know, but for this course the notation we are going to use is something like this. So x, y and z, which is our original coordinate system, x prime, y prime and z prime is our new location. So let me draw this also. So the direction cosines that are going to relate them. So x to x prime will be related using the L1, similarly M1 and N1 for the y and z direction. And if you want to relate these direction with the y prime, then we are going to use L2, M2, N2, and similarly for the last z prime direction we are going to use L3, M3 and N3, right? So for this course we are going to use these notations for the projections on other. And other thing I hope you remember about the direction cosines basic functionality or basic relation is that we have summation of squares. If you want to write, then this will be 1, right? In our case, our I is going from 1 to 2 to 3 only, and similarly other 3 relations I will just write it down, and I am assuming you guys are remembering these from your earlier classes. Because whenever we are going to work with the stresses, you should know how to manage the direction, and direction directly relates to our direction cosines here. So this is all that we are going to discuss about the direction cosines. But please remember what L, M and N stands as per this course is, and these relations that are written in the orange color, and I am assuming that you will be knowing all this, because whenever stress is there, the subject of transformation is there. Basically, if we know a stress in a particular direction, and if, or in other words, if you want to know stress in some arbitrary plane, then most of the time for transformation, basic understanding of the direction cosine is needed. So now coming back to our original coordinate system that we have used, you have the horizontal as x, vertical as y, and out of plane as z, where you also have the unit vectors in those directions as I, j and finally k, right. So what we are going to show is, we are going to draw a arbitrary stress vector, and for that, since we have already established our coordinate system, we'll write it out, sorry, we'll draw it out. Let's say we have stresses in these three directions, which is sigma xx, sigma xy and sigma zz, right, or zz. And let's say we are drawing a stress vector, arbitrary selected stress vector, let's call it sigma for right now. So if you want to see, you can also think is somewhere within the cube that we have drawn. So I'm just drawing the dotted line to show that you can also consider this as within the cube of earlier presentation. So this lies within that cube, let's assume, and now we will write out whatever the assumptions we have taken. Before moving further, so what we have said is that I, j, k are the unit vectors which are related to the choice of the coordinate system that we have made, which is x, y and z direction, right. So just a second. Second thing, we are going to write about sigma x, sigma y and sigma z. So we are related to the coordinate system we have chosen. So let's assume sigma x, sigma y and sigma z are the stress vectors on the plane the assumption that we have already seen earlier, where we have drawn the cube. So unit vectors and the stress vectors are now defined, and if we want to write the sigma x, sigma y and sigma z in its component, when we know the unit vectors I, j, k, we can simply write like this. So So all the stress vectors in the direction or the axis of our choice x, y, z, we have divided them in their individual components using the original stress tensor that we have discussed, and you can see the components of the stress tensors are there along with the unit vectors, which are essentially providing the directions or directionality to our stress vector. And now what we are going to say is, now what we are going to do is we are going to select a plane which is arbitrary and which with a unit normal or a unit normal as a n, and we'll now come back why that is important. But just for a second, you can assume there is a plane which is arbitrarily located in this coordinate system and which has a unit direction or unit vector n, normal unit vector n. So let me write that also. And this unit vector is related with ijk with a direction cosines that we have discussed. So we can also write this unit vector as so now this unit vector n is acting as a bridge, or basically it's providing us something where we can relate both the situation, whether it's a stress vector in the direction or xyz where we know the situation or where we know the values, or if this is a vector on an arbitrary plane, stress vector on an arbitrary plane with a unit normal. So if we assume that we have the information lmn, then so here also let me write, these are the direction cosines, right? So as sigma x, y, z are related to the x, y, z direction, what we are going to say is the sigma p is a stress vector which is acting on a plane that we have selected, or let's say it can be a plane P, just for the notation. So we'll just write also let sigma p be the stress vector on that plane. So knowing the direction cosines, we can write or we can relate it with the sigma y and sigma z, right? So now what we have done is we have related an arbitrary plane with the information that we already have in a coordinate system of our choice, provided we know what L, M, and N are. So now what we can say is we can further subdivide, and now what I'm saying is, what we are saying here is that sigma p has the projection on the x as sigma px, its projection on y is sigma py, and projection on the z as sigma pz here. And if you want to further subdivide those components which are the projection on the x and this, with the help of the unit vectors, what we can write is okay, we can write this relation. Okay, so now what we are going to do is we are going to write our sigma p in terms of its component that we have done, and now we are going to subdivide their components with respect to the original sigma xx, sigma xy and sigma xz, and along with their unit vectors. And this exercise we are doing, the purpose of this exercise is to show that once you have a relation, other coordinate, even if you change your coordinate system or if you basically rotate, translate, you can still find the stress state in the other coordinate systems. So once so far we have written sigma p in its subcomponent, now we are going to write its subcomponents one by one. So let's write first sigma px. So that will be L sigma xx plus m sigma yx. Lm and are our direction cosines, and then yz or yz. Similarly, we can write other remaining components, which is sigma y, and that will be L sigma xy plus m sigma yy plus n sigma zy, and similarly the last component, which is our sigma pz, and let's write it again in terms of xz plus sigma yz plus sigma zz. So now we can write that, let me write it out. We can calculate the stress components in any arbitrary plane which is defined by the unit normals. Along with their direction cosines. If the stress tensor is known, basically if the components of stress tensor is known, so if 6 component, in case sigma ij is equal to sigma ji, so now if we draw a plane which we are talking about, let's say it's an arbitrary plane, okay, and now we'll draw 3 lines which will be representing my normal, Then let me first draw this thing. So this we have already drawn earlier. So if we know the normal and shear, then what we can say is we can simply write the relation which can use the knowledge of direction cosines and the known stress tensor matrix to find the stress vector in a given plane. So let me write this out. If we assume a plane as shown, and this is where we have shown the plane, and if we also let our normal component then the projection of sigma p, which is our stress vector, in the direction of unit normal or in the direction of, let's say, n, can be simply written as just using the simple law of direction cosines. So this is for the normal component, right? But if you look carefully, we have also shown the shear component. And when we are talking about the shear component, then we can simply write here. Actually, shear is much easier. Magnitude of the shear stress can be calculated. So the PS component from the just the little triangle we have shown, right? If you know the stress vector and the normal component, finding out third is not difficult. And if you want to expand it further, you can write like this. So here is a generic definition and derivation of the stress components and their projection is finished. So now what we know is what the uniaxial stress is, what is the stress at a point, what is the stress tensor, whether sigma ij and sigma ji condition can be used or not. So depending on whether you can use, you will be needing 6 or 9 components. And then we have seen, if we know the stress in a coordinate system and you select any arbitrary plane, if you can relate that plane with the coordinate system using the unit normals, you can obviously find the stress vector in that plane with respect to that plane also that we have shown. So these are the primary derivations, or basically primary information in the stress which is known. So after this, what we are going to do is we are going to cover few basic definitions of stress, because when we are saying stress, there are multiple types of definition, or basically depending on the convenience, we have multiple definition for the stresses, and I will just write the most useful or the most commonly used terms when it comes to the stress, and we'll see what those terms refers to or what those terms related to. The first important definition, or one of the important definitions we are going to see, is the principal stress. Essentially, the principal stresses are the components in the normal direction when you have no shear. So let me write the derivation of principal stress and then we'll discuss it. So for keeping it general, we are going to select an arbitrary body, again subjected to an arbitrary loading condition or the forces. So what we'll say is, if we choose we have selected a point in a body and which is again subjected to the arbitrary state of stress, then there will exist three mutually perpendicular directions. Planes at that point without any shear. And the normal stress components on those planes are the principal stresses. Should write planes, not points. Points on the planes. So for what we have said is, we apply, or if we deform a body, at every point there will exist three mutually perpendicular planes where there will be no shear, and the normal stress component in those planes will be the principal stresses, and the planes themselves will be known as principal planes. Also, the axis associated with those planes will be known as the principal axis. So I'm just going to write that also. These planes are called principal axis. So now we'll go back to our stress vector, that was sigma p, and we'll relate with the principal planes. So let's assume the same vector again. Stress vector sigma p principal plane is by n, right, where n is, we know what n is a unit normal, we have already seen, and sigma is the magnitude of sigma p, which is our stress vector. So we'll take the projection of sigma p, thus the projection sigma p along our x, y and z direction So now you might understood why we used, or why I emphasized on L, redefining basically refreshing your memory regarding the direction cosines, because we are using it again and again in relating different situations. So if we do that, then what we can write simply, so I'm just writing in terms of LMN the different components. So for those who are thinking from where we have got this thing, let me outline this box. Okay, if you are still thinking how we got this from the projections, I would just refer you guys back to the work that we have done here, and this will make you so clear. So it's the same concept. Here we have written the subcomponents, right? So this is the exact same thing that we have done here. So now what we can see is that we have three equations along with the direction cosines that we claim that we know, and now comes the big question, how we are going to solve, because if you see we have three equations and all of them are set to 0, right? Because if you look at the equation carefully, you will realize for the solution to exist, there is only one possibility, that determinant should be 0. If the determinant of this matrix that we are going to write is not 0, the solution will not be unique. So let me write this out. Right, and the reason is because is not possible. You cannot have L, M and N all equal to 0. Reason, they are bound by a law which state right. So this requirement guides your solution, that determinant should be 0. And now let's see, if we equate the determinant to 0, what will happen. So just a second, let's first write it out, how it looks if we say determinant is 0. That's how it will look. And if we want to solve this above condition that we have stated, we would be expanding the determinant, and if we write in the short form, after expanding we can write what we get is this. So if you equate the determinant to 0, ultimately you are going to get this equation, and this is very standard equation in solid mechanics when it comes to the principal stress. Here I1, I2 and I3 are known as stress invariant, because they will not change regardless of the choice of the coordinate system. For any coordinate system, you will have the same I1, I2 and I3. So let's write this out also. Invariance of stress so in terms of the stress tensor component, I1 is written like this. It's mere the summation of your diagonal terms, right? I2 can be written like this. Please remember, we are solving the determinant. Okay, just a second. So it's kind of getting big, but solving is necessary. and my third stress invariant is the matrix which you are already aware of. So basically determinant of this matrix. So if you calculate stress invariants I1, I2, I3 and then come back and solve this equation, whatever the roots of this equation you are going to get will be the principal stresses. Essentially, they will be the stresses in a plane where shear stress will cease to exist. So roots of the above equation, let's call them as sigma 1, sigma 2, sigma 3 are three principal stresses and let me write about the stress invariant also. As I said, they are independent of your choice of the coordinate system. So let me write this also. I3 independent of choice of the coordinate system or coordinate axis, however you would like to state. So we have seen the stress invariant, how it looks if we are writing in terms of the stress tensor component. But if you already know the principal stresses, then writing stress invariant is very easy. So the way in terms of the principal stresses, let me write this out. In terms of the principal stresses, we can write the first invariant is again the summation. The second invariant gets much simpler. So now we have the principal stresses as well as the stress invariants. Another use of a principal stress one is this: you can find the maximum shear stress, which is tau xy or sigma xy, let's say. So just a second, let me write, draw a line. Just it's a small note, so I'm drawing a line. So we are saying maximum shear stress first time we are using tau, but we know sigma shear, sigma xy can be also written as this. It's up to you. Is the difference, is the half of the difference of maximum and minimum principal stress. So here the sigma 1 is the max, let's say, and the sigma 3 is the minimum shear stress. So if you know the principal stresses, you can find the maximum shear stress just based on the subtraction and the taking the average of the difference between maximum and minimum shear stress. So this is all about what we are going to say about shear stresses, about the principal stresses. Now we are going to come to another important part of the stress family, and which I will show you by writing. So we already know that a stress tensor looks something like this. Okay, let me rewrite the stress tensor. We know we have just a second. I have to change the color. Okay, so if this is my stress tensor, right, which we have written so many times again and again, yx, yy, yz, sigma zx, sigma zy, and sigma zz or zz. We know if we have this, we can split in two parts. You can split in multiple parts, but right now we are just splitting in two parts, and we are saying we are dividing it in a manner where it looks something like this. We'll come to it what it is, but just right now we are writing. So another family we are creating with x, y, y, z. And we are saying that just a second. So one is this, and essentially actually it's looking in one line, so let me rub and it is, so to avoid the confusion, let me write here. This one looks like this 0 0 0 p 0 0 0 p. So now the reason of us dividing the stress tensor in a manner is this. From the simple stress tensor, let's say this is our stress tensor, we have gotten two components. First component we are going to name it as deviatoric stress tensor, and the second one is hydrostatic stress tensor. We also sometimes call it as a volumetric stress. Hydrostatic stress tensor, volumetric stress. So what is the need of dividing our stress tensor in these two components is as following. So now we'll just write what is the need is. So we'll start with the second term as it is simpler to explain, then we'll come to the first term. Because when we say we are dealing with hydrostatic stress, we should know that it is responsible for change in the volume, though it's not responsible for change in the shape, but yes, responsibility of changing in the volume lies on the hydrostatic stress. So we can write is responsible because, as we have already discussed, when you apply a different magnitude of stress state, the specimen may undergo a deformation or the change in the volume. So what we are associating the second term or hydrostatic stress is that it is responsible for change in the volume. and in general it's very easy to find because it's just the mean of the diagonal terms of the stress tensor. See, you should understand carefully, when something breaks or fractures, two important things happens, right? First, it starts with the deformation or the volume change, and then slowly it leads to fracture. But here we are going to write the hydrostatic stress, and if we look carefully, we have just talked about the stress invariants, right? If we want to write P in terms of the stress variant, we can easily write like this. So if you know the first stress invariant, you know the P. In other words, you can define the hydrostatic stress tensor, right? So where I1 is our first stress invariant. And if it's just the 1/3 of the stress invariant, then it also means that P itself is not connected to the choice of the coordinate system, right? Because I1 is independent of your choice, so that turns P also is the independent of the choice of your coordinate system. So thus P is independent we should be also able to see that it is equal in all the direction. So if we look carefully, we are calling it hydrostatic. And if you take the original cube that we have drawn earlier and you let that cube sit, let's say in the below half meter of water, then obviously you will note that all the 6 faces will be sharing the same load, or in turn same pressure, right? So it is acting equally in all the direction, thus the hydrostatic. Now comes the second term, and that will also tell us more why we have divided the stress tensors. So let's write this. The main reason behind dividing the stress tensor that many failure mechanism are caused by its components. If you have a hydrostatic state of stress and you keep increasing, basically let's say you have a submarine and it dives down the sea, right? Each submarine is rated for certain pressure tolerance, and if that submarine keep going down beyond that load, what will happen? You have a hydrostatic pressure acting all around the submarine, and ultimately the structure will give up and you will have a catastrophic failure. It may buckle or it may yield a lot, and then finally it will crack or fracture, and thus the failure. So that is because of the hydrostatic, but there are other failures that we have seen that results from the change of shape, right? And if you have that kind of failure, then the first term comes into the picture, and the first term is, as we have stated, deviatoric stress, right? And deviatoric stress in the here, if you look carefully, we have written in terms of the d, right? But the other way, if you look, this is the where we have written the first matrix or the first component of the stress tensor distribution. Then we can write this also in this fashion, because we know the other side is only the diagonal terms of P. We can write like this. I hope all of you can understand why we are writing the D in terms of like this, because if you remember carefully, when we were talking about the principal stresses, we use the same technique, or let's say same pathway, to get to the solution. And if you look carefully, this is I am talking about the diagonal. If you look carefully here, the diagonal terms here, right? We are subtracting sigma from the diagonal terms, and the only difference here, what we are doing is, instead of sigma you have the p. So nothing has changed, concept is same, it's just the choice of your constant, let's say this. So the solution will also be in the same manner, right? So first let me write about the deviatoric stress, and as we have already stated, it is the main reason, not the only reason, but the main reason So we can solve using the same analogy as the principal stress. So that's right, we can using the same approach. So we'll just change the constants, otherwise you are smart enough to understand the solution is same. So if we solve that determinant, what we are going to get is something like this. Please remember, earlier we were writing sigma, here we are writing d, nothing has changed. So essentially the concept remains the same. If we go back, I think I might have missed the cube term. Let me check, please. No, I have written here. Okay, that's good. So the same equation, just in the changed constant form, and thus the concept is same. So the invariants will be there, where what we are going to write this is, these are the j's, not I. So where j1, j2 and j3 are the first, second and third deviatoric stress invariants. So same thing, right? So I'll just write in the index notation just for the fun, but please remember, in the entire course we are going to explicitly expand the terms. We are not going to use II and JJ. This I will leave for the other courses, but just for the fun here we are going to write in that manner. So that is the first term, and second and third are similar. So I will leave that for you guys to fill. But what I will do is I will write j's in terms of the, yeah, we can have little fun here. We will write deviatoric stress invariants in terms of the principal stress invariants, and let's see how they look. If you expand and rewrite, you are going to end up on this relation. So this is stress invariant of deviatoric stress versus principal stress, j's and i's. And similarly, if you want to write the j3 term, it will be slightly involved, but once you expand and contract, you will see that's what we are going to get. So that is the split of stress tensors in two components, and the explanation why these two components are important. The first was responsible for the change in the shape, deviatoric stress, and the second one is responsible for the change in the volume, the hydrostatic stress. And if you realize, most of the engineering failures will fall in one of these two categories, where the fracture or the crack or the failure get initiated. So this is we are almost at the end of the stress, where we have covered what we are going to use. But let me come to the last important terms in the stress, which is the plane stress. So let me write that part, then I am going to explain what is the plane stress and why it is important. So now let's consider a plate which is big in dimensions, in x and y, which are the width and the length, but narrow in the thickness direction. So this means it's a prismatic plate which is thin in nature. And what we are going to do is, okay, let me write it out first, then we'll just write. So we are considering a thin plate, and out of that thin plate so we are putting our central plane. So the plane of our interest, basically xy plane, will lie at the center plane of the already thin plate, and this plate we will assume it's under the in-plane loading conditions, or it is subjected to the in-plane forces. Just a second, located halfway through thickness, subjected to the in-plane forces. Okay, so plane forces, let's go to the second page, and we are going to draw it. So what we mean by this is, we have a thin plate, it's a prismatic plate. This means the dimension remains uniform throughout the geometry. So we have selected a thin plate as shown in the figure, and we are using this thin plate in a half manner. So basically we are again dividing this thin plate as shown in here. Okay, so let me complete the plate, otherwise it looks confusing. And what we are doing here is, we are going to place the coordinate system at the center section of the plate in a manner as shown. So x, y, and out of plane is the z. So we are following this notation. And now what we are going to do is, we are going to write some assumptions. So we are saying that first one is, this plane of interest xy plane is in the mid section of this thin plate, and we are going to put the coordinate system at the center of it. So let's say, let the thickness, direction, coincide with the z-axis, second assumption that we are going to write is very important, and we are saying, if there is no load, you can also say force, in the out of plane direction, in the z direction, then it may be assumed that throughout the plate stress components related to the out of plane dimension are negligible, and they can be equated to big zero. So this is the plane stress assumption, right? And where, if you want to write in other words, we can say, we are assuming sigma xx, sigma yy, and sigma xy to be independent z-axis. So again, this is an assumption. It's not accurate assumption, but it is an assumption. And in most cases of thin plates, it is sufficient assumption, because what we are doing is we are decoupling the stresses in x direction, y direction, and xy direction from the z direction. And second thing we are doing is we are setting all the stress components that are related to z direction, whether it's sigma zz, sigma zx, sigma zy, equal to 0. In real case, even in very thin plates, there are a very small magnitude of stresses available under sigma zz, zx, zy, but for practical purpose, it's safe to assume, or it's safe to neglect them as 0. So with the above assumption, what we can say is so only two variables of importance are left, and in such scenario, such stress state, we call it as a plane stress, because we are considering only a plane. So this means for considering the stress components, we are only considering two directions, x, y, as the choice of our coordinate system, and the direction cosines for such plane stress condition can be simply written like this. So if we say we have x to x prime and y to y prime with angle theta or rotation theta, then we can say direction cosines for plane stress so is equal to 0, because we don't have this third direction to be considered. And 3 is 1 because it's a projection over itself, so you have the unit number there. And if we assume the plane stress conditions, then stress invariant also will be reduced. So if you want to write only the summation of the first two diagonal terms, we don't have the third term to consider. Actually, we are ignoring the third term. So the stress invariant 2 or I2 becomes much easier to calculate. So this is the plane stress situation. But please remember, plane stress situation is not a general situation. It's a situation that depends upon a particular set of conditions. the member on which you are applying this condition is supposed to be thin. Basically, one dimension is extremely small in comparison to the other two dimensions. A member has to be prismatic, and the assumption that we can decouple the stresses from the third direction, though may not be exact or accurate, but they are acceptable and they give us the results reasonably well. Earlier time, when we didn't have the enough computational power, this concept was exceptionally used to get the results. Nowadays also, in many techniques, whether you are using finite element analysis or something else, and you are doing other numerical modeling, in some situation plane stress assumption is extremely useful and valid. So with this, we are going to definition of one of the stress, and the reason I am covering in this in class because it's most commonly used, and sometimes it's used as a benchmark to decide whether the component you are doing the analysis or you are using for certain application will survive or fail under the uses condition. Most of us already know it well, and it is known as von Mises stress. Generally, it's marked as sigma v. You can use any notation, but we are not going in detail of this. We will just write it out what it is and why, where it can be used. And also please remember, all the material that we have covered in the stress is extremely useful in deciding when the material is going to fail and how the material is going to fail. This is one of the most common stress term that is being used. It is useful in determining will yield or fail when you apply a certain loading condition on it. One of the reasons of the popularity of von Mises stress or the criteria is that it gives you one number. So it's kind of oversimplify the situation. When you're doing the detailed stress analysis, you actually needs to go much further than this. But what happens is, it really gives you basically a place where you can start your comparison or a threshold number, and when we want to write this von Mises stress in terms of the stress tensor component, we can do it in a manner like this. So is the subsequent difference of the diagonal terms, square of the subsequent difference of the diagonal terms, plus the 6 times square of the shear stress terms, and then we take the mean of it finally under the square root. So though it looks like there is a number of variables, but it's actually simple. And if you want to write in terms of the principal stress, let's say you know already what the principal stresses are, then finding the von Mises stress becomes extremely easy and simple to remember. So let's say the square root term is still there, but it's only the square of subsequent summation, sorry, square of difference of subsequent summation. Just a second, let me erase and rewrite it. It's a lot of, okay, now I'm going to rewrite as the square of the subsequent difference terms being added together. So last term should be sigma 3 minus sigma 1 square divided by 2 and taking the square root. So this von Mises term, though if you want to go in detail, it will be in advanced solid mechanics thing, but as far as we are concerned, we are taking it as a number which will help us in deciding whether the failure is near or it has been achieved. So, and how we are going to accomplish it? It is accomplished by comparing says yield criterion. See, most common way of using the von Mises stress is by comparing the number against the yield stress of a given material that you are interested in, and if it is bound, then obviously it's not safe to continue. So I'll just write this also. If sigma Vm is greater than the simple yield material is likely to yield, or material is expected, we can say, or fail, whichever you would like to say. Now let's cover the last two topics of this class. These topics will be covered in detail later, but since we are talking about the stress, so the second last topic that we are going to cover is the stress concentration, and the last topic will be stress triaxiality. So before we end this class, these are the only two topics left. So let's cover them. So intuitively, we all know what the stress concentration is. Essentially, it's a site or a location, we can say a point or a position in a body where the stress is relatively or comparatively higher in comparison to the other states or other sites of the body. Reasons are well known. If there is a sudden change in the geometry, if there is a crack or a let's say orbit change in the cross section or anything like that, even the corrosion can result in the stress concentration. So let's go to the stress concentration. We are writing it is a accumulation of stress in a structure or body, we can say, at certain points or locations. And reasons can be many. As we said, we can first can be the sudden change in the geometry. And sudden change in the geometry can be like sharp corners, holes, etc. And other option can be the presence of the cracks or dislocations or discontinuities, whatever we would like to say. Essentially, in general, stress concentration is quantified by using a number, and which is the stress concentration factor, because different kinds of defect or different kind of sudden change in the geometry will result in different stress concentration. So to quantify the effect, a number is used, and which commonly is referred as stress concentration factor. So, and also I forgot one thing, stress concentration is also known as stress riser. Also known as stress riser or stress raisers. It's just different names used in the different parts of the word. But now we'll come back to the important constant that we were talking about. Which is stress concentration factor. It actually quantifies the effect of the any orbit change in the geometry or discontinuity. So let's write how we define it. It is a simple ratio of the maximum stress that you are going to get with the reference stress, and we'll draw a diagram to just make it clear what we mean by these terms. And in general, a well-known solution is for a circular hole, the value of kT is 3. We will see the derivation of this also during the part of the course. But let's see how the circular, let's say, hole in a body will affect the stress distribution or overall stress distribution in the body. So for the understanding purpose, let's assume you have a thin plate as we are drawing. And let's say this plate has a hole in it. And what we are going to do right now, we are going to apply a loading that will create a reference stress. Or let's say we are applying the reference stress, which we are calling it as sigma REF in a body. And we want to see the effect of a hole, whether the hole creates or how the hole affects the stress distribution in the body. So for this purpose, what we are going to do is, we are going to first select a coordinate system so that we can plot the distribution of stress. And if this is a coordinate system of our choice, which we are placing on the boundary of the circle in the center plane of a plate, and now if you want to know how the stress distribution will look, it will look something like this. And in the part of the course, we'll write the codes also to see how the stress distribution occurs even ahead of the crack tips. But just for now, what we are writing here is a distribution of stress. So let's say this is my sigma reference, and that's how it's going to look. If you want to draw stress distribution on the location when we are going away from the circle boundary to the outer boundary of the specimen, that's how the stress distribution is going to like. Initially, when x is very small, you will have a higher stress. We are calling it as stress sigma max, and the reference stress is the applied stress that we are going to apply. So this way we can see when we are closer, this zone, or let's say this zone, will have a higher stress than the surrounding area. And how it affects? The worst thing is, it helps failure by promoting the crack formation or its propagation. So in general, we tend to avoid the defects or the sudden change in the geometrical boundaries of the structure or any part that we are using. We'll come back to this thing in detail when we'll be seeing the other points of this course, but just now we are referring the stress. So we'll move to the last point of our interest, and that point is, which is also important for us, stress triaxiality. So if we just go by the definition is simple. This word essentially represents the ratio of mean stress or the hydrostatic stress upon the equivalent stress, which is von Mises stress. So it tells you how much effect a hydrostatic stress has in the overall state of stress. And why it's important? Reason, this term alone mostly defines whether your fracture or a crack is going to occur in the ductile fashion or the brittle fashion. So basically, if the term goes higher, you have one either ductile or brittle, or if it goes lower, you have between ductile or brittle. So more higher the term, more you are moving towards one of the either brittle or ductile that we are going to discuss later. But this is again just a one term that is the indicator of how the crack or the fracture is going to occur. So just for the stress analysis purpose, we'll write a brief description, and later in the later classes we'll discuss in detail. To the equivalent stress. So it's again generally used as a number. So we'll write as a triaxiality factor and again we'll also write out its importance when it defines whether a brittle or a ductile condition will take over. So or ductile and also we are going to cover this in the later classes, because we'll discuss about how this term is directly connected to the fracture and how this term is evaluated. So in this class, guys, we have come to the end of this today's class. In this class we started from a stress at a point, then different stress components, how they are projected using the direction cosines. Then we went to the different kind of stresses, whether it's a principal stress, stress invariants, how we can divide the stress tensor in hydrostatic stress and deviatoric stress, why they are responsible, and then after a few iterations we are going to finish today's class with the von Mises stress. So as far as this course is concerned, we are not going to go in further detail in the stress region. So with this, guys, thank you, and I will see you in the next class. Thanks.